Hello, and welcome back to my YouTube channel. My name is Professor Gavala, and today I'll be talking to you about a very important concept in electrical engineering called a digital to analog converter, specifically the R-2R ladder digital to analog converter, or DAC. And first, we want to talk about the pros of this configuration for a DAC, and it's that it contains only two value type of resistors, as we will see in the schematic drawing. It can easily be fabricated using a CMOS process. It can lead to high accuracies, to high accuracies. It is easily scalable to any desired number of bits, and R out is always equal to R, no matter the number of bits used. So I'm not going to dive too much into a lot of details on what a digital to analog circuit does, but in brief speaking, a DAC, its inputs are a digital signal. So this is like a 0 or a 1, and its outputs are a analog signal, which is a voltage, so a voltage value. And essentially, the circuit we will be analyzing in this video is just the 3-bit R-2R ladder DAC with an amplifier at the output. Where this DAC has certain inputs, and the inputs are the bits, where BO is the least significant bit. B1 doesn't have a name, it's just B1, and B2 is the most significant bit. And if we have a circuit that looks like this, where this is V reference or VDD, and this is a ground connection, we could say that the input of this DAC is B0, B1, B2, where B0 is equals to 1, B1 is equals to 0, and B2 is equals to 1. And again, we get that because B0 here is connected to V reference, and whenever we're connected to a voltage, that just means that we have a high in terms of our digital signal. And here we're connected to a ground, so that just means we have a low or a zero. And here we're connected to, again, VDD or V reference, so that means that we have a high of 1. So this is our input in terms of digital or bits. And we want to generate an output. We want to generate an output signal. And this is the point of this video. Or the key point of the video. In order to generate what the output will look like, we start off by finding what's called the R Thevenin of this circuit, and we make a dashed line around this circuit. Where R Thevenin will be looking in here, what is RTH? So in order to do that, using our previous knowledge of circuitry, we can write or draw the following. Where we ground all our voltages, so Vref is grounded. And we look in, this is ground, and we look in and we ask what our RTH is, given the following resistor values: 2R, 2R, R, 2R, R, and 2R. And this is one of the benefits of this circuit, is you only have two resistor values. So if you pick a resistor value of 10K ohms, your other resistor value will just be 20K ohms, or 2 times 10. So that makes it easily fabricated, which leads to high accuracies, as well as low in cost and not as cumbersome. So in order to do this, we break this circuit down into 3 different circuits, where we consider the green to be R1 TH, and then we consider the blue this point here to be R2 TH, and lastly we consider the red, which is the entire circuit, to be right here, and this is R3 TH, which is equals to RTH. So to first begin, let's start with the green, or R1. And R1 is just a circuit that is made up of a 2R resistor and another 2R resistor. And from our knowledge of adding resistors with a extraordinary node attached to it, this is in parallel. As a result, R1 TH is equals to 2R times 2R divided by 2R plus 2R, and this equates to being R. How you see that is, this is 4R squared over 4R. You cancel this, this one cancels with this one, and you get R. So now R1 TH is equals to R. So the equivalent circuit now is this resistor, another resistor, and 2R, where this point, or I'll draw the rest of it, 2R, this is R, this is R, this is R1TH, which is also equals to R. So essentially, as you can see, we've gone from here, and now R1TH, which is the point there, has been simplified to just this resistor. And now we want to solve for our blue dash line, which is R2TH. And this is equals to, so this is here R2TH. So R2TH is equals to R1TH plus R, because this is in series with each other, in parallel with 2R. And that's 2R's coming from here. So how do we do this? So R1TH we know is R plus R in parallel with 2R. And now we know 2R in parallel with 2R is equals to R. The reason we know this is because we did it up here. This evaluation was the evaluation of 2R in parallel with 2R. And so we get that R2TH is equals to R. So now our equivalent circuit can be drawn like this, where this is R2TH, this is R, this is 2R, and this is basically our R3, right? Located here, R3TH. So I'll do it in red. This is R3TH, which is equals to RTH. So, and again, if we do this, we get that R3TH is equals to R2TH plus R in parallel with 2R. And this is simplified to R plus R in parallel with 2R, which is then 2R in parallel with 2R, or just R. So this R is equals to R3TH, or just RTH. So now we understand that our R Thevenin is equals to R. And this, by the way, is also equals to R out from our original circuit, which was located right here. This RTH is located here, which is equals to R out. Now, in order to find the voltages of this circuit, we need to consider that if we have a circuit that looks like this, again, this goes to the op amp, and this goes to our VREF. We could say that B0 is equals to 1, B1 is equals to 1, and B2 is equals to 0. So, and now we want to find, what we need to do is we want to find our VTH1, VTH2, and VTH3, and use superposition to find VTH is equals to V1TH plus V2TH plus V3TH. All right, I think I put the 1 on this side, but I guess you get the point. So essentially, just writing it out, you could find the voltage at the output by using what's called superposition theorem. Find it. So we'll begin by, let's say we take 0, 0, 1, where this is B1, B2, this is B1, and this is B0. This is the least significant bit, and this is the most significant bit. We can then say that we're going to get a circuit that looks like this is V out. So our B2 is grounded, B1 is grounded, and V0 goes to our reference. Again, these resistors are the same. R-2R, R-2R. And what we can do is we could find VTH1 that's located right here by making this circuit equivalent in terms of a circuit that looks like this, 2R, Vref, where this 2R value is located right here, and this 2R value is located right here. And what we want to do is we want to find VTH1, and we get that VTH1, because of voltage division, is equals to 2R Vref over 2R plus 2R, which is equals to Vref over 2. And again, the proof of this is 2R Vref over 4R. So then the R's cancel out. This is 1, this is 2, this is 1/2 Vref. So now we have VTH is equals to 1/2 Vref. What we can now do is redraw this circuit here. And this time, and also we know, let's just note this, that looking in, RTH1 is equals to R, and this was proved earlier in the video. Now we can redraw that previous circuit as something that looks like this. Where this is R, right? This is equals to RTH1. This is R, this is 2R, this is R, and this is 2R. And this is Vref over 2 now. And this is, and then we want to basically analyze now this portion of our circuit. And we consider this V Thevenin, the new V Thevenin 2. And so what we can do is, again, we could use superposition with this red part and simplify our circuit to be 2R, 2R, and there's a Vref here, and this is VTH2. And again, we'll see that, and this Vref now is Vref over 2. And again, we'll see that VTH2 is equals to 2R Vref over 2 divided by 2R plus 2R, which is equals to Vref over 4 when you do the math. And again, RTH is equals to 2R in parallel with 2R, which we proved earlier to be R. And what you can do is, without having to redraw it, you can combine this circuit, or I'll do it one more time. You can combine this circuit to look like this now, where this is RTH, which is equals to R, RTH2, which is equals to R, this is R, and this is 2R, and this is VTH3. This here now is going to be Vref over 4. And what happens is when we look in like this, we get VTH3 to equate to 2R Vref over 4 divided by 2R plus 2R, which is equals to Vref over 8. And RTH is equals to 2R in parallel with 2R, which is equals to R. And again, we proved this earlier. So now we have our circuit, our Thevenin circuit, which says that our Thevenin circuit, which says that for this style of bits, for B2 is 0, 0, 1, we get this is RTH is equals to R, and VTH is equals to Vref over 8. And this is our circuit. Now, what we need to do next is solve the same thing for B2, B1, B0, but this time around, B0 is equals to 1. And what I'll do here is just draw out the circuit, how this looks. So B0 is grounded, B1 is at Vref, and B2 is grounded. 2R, 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 R, and R. And essentially this circuit here is discarded because it's not pulling any current, because it's grounded here and it's grounded here. So what we can do now is write our circuit as something that looks like this. Something that looks like this. And without proving or doing step by step how we did before, we can look in here and we could find RTH and VTH, where this is Vref. And we find that RTH is equals to R. And again, we proved this on the earlier in the video. And V1 is equals to Vref times 2R over 2R plus 2R, which is equals to Vref over 2. And let's say that this is V1. And then V2, which is equals to VTH in this case, is equals to Vref over 2 times 2R divided by 2R plus 2R, which is equals to Vref over 4. Last but not least, we next want to prove that for B2, B1, and B0, where this is 1, 0, 1, sorry, this is 0, 0, 1. So essentially now B2 here is 1, B1 is 0, and B0 is 0. So this essentially now becomes a circuit that looks basically like this. This is 2R, this is R. That looks like this. R, this is R, this is Vref over, this is just Vref. We can show that VTH in this case 3 is equals to Vref over 2, and RTH is equals to R, which is proved earlier already. Now, we can conclude the following based on our analysis. Therefore, and let me use a smaller pen here. If we have a table B1, B2, if we have a table B2, B1, and B0, so a 3-bit input, 1 0 0, 0 1 0, and 0 0 1. We've proved that this is Vref over 2, this is Vref over 4, and this is Vref over 8 plus Vref over 4 plus Vref over 2, which is equals to 7 over 8 Vref. And now let's say we have made a mistake here, sorry. 0 0 1 is Vref over 8, but then if we combine all of them to be 1 1 and 1, Vref over 8 plus Vref over 4 plus Vref over 2, and this is 7 over 8 Vref. And now in general, we can generalize this equation. When n is equals to 3, Vref V0 over 8 plus V1 over 4 plus V2 over 2. And so now we can generalize this and say that for n is equals to n, number of bits, Vr-2r is equals to Vref Vo over 2n plus V1 over 2n plus 1. Sorry, this should be n minus 1. N minus 1 plus V2 over 2n minus 2 plus dot 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 plus Bn minus 2 over 2 squared plus Bn minus 1 over 2 to the first, where, again, this is the most significant bit and this is the least significant bit. So now a quick example of this, given the circuit where we have Vref and we have a voltage output here, V out. This is the circuit from before. So if we say that we have VDD is equals to 5 volts, or again, this is Vref is equals to 5 volts, and we want to find the least significant bit given a 5-bit DAC and a 10-bit DAC. For the 5-bit DAC, the least significant bit will be 5 volts over 2 to the 5th, which is equals to 5 over 32, or 0.156 volts. And for the 10-bit DAC, the least significant bit will be 5 volts over 2 to the 10, which is equals to 5 volts times 1024, which is equals to 4.88 volts. So as you can see, we've gone from a single high or low bit. So 5 volts is considered 1 or high. And now we're at a voltage. We've gone to an analog output. And here, all this is saying is, if this is RF, a feedback resistor, all this is saying is V out is equals to minus RF over RS, or R source, so the R coming in from here, times V out, which is this value we've calculated here, these values. And that's just basically inverting op amp, which I'll talk about in another video. Please don't forget to like, subscribe, and share. And if you have any questions, please leave a comment down in the comment section below, and I'll be sure to get back to you. Thank you. Have a wonderful day.